All right, so today we're going to talk about solutions and concentrations. You have a really simplistic note sheet. The intention is that you're going to write a few things on the left side, not a lot, and then we'll do a couple problems on the right side. Okay, so that's kind of my hope. Hopefully it'll work out that way. Again, if you don't have a calculator, let's get one out. So we're ready to go. All right, so concentrations. And I'll let you know what you need to write, okay? Need to get through today the idea that a concentration, you have context in this already, is a ratio. So we're going to do something that's kind of silly. Let's talk about fish and volume. So if I talk about a concentration of defining it as number of fish over how many liters, again, just for observing today, or so far. And I say that this thing is 1,000 milliliters, and I have, oops, I forgot what I'm doing here. I have one fish over 1 liter. So today we really have to get down the idea that 1,000 milliliters is a liter. So if I have like 2,500 milliliters, that's 2.5 liter. One fish over 1 liter, we have to come up with some sort of a unit. Well, maybe we call it Fisher or Fisher. Who knows what that's called? But it's 1 over 1, so the math is just 1, right? If I add 2 fish in the same volume, then I have 2 fish over 1 liter, right? So then it would become 2 Fisher, right? So we keep moving forward. A couple of weird, just simple examples here. Also, now I have 4 in the same volume, right? So now I have 4 fish over 1 liter. So we're going to call n as in the number that you have of something. It would be 4 fish are. And the bracket sometimes is considered concentration. Okay, well, all of a sudden you go bigger. You put that many fish. You're like, oh, it's got to be a bigger concentration. Well, here's the difference, though. I'm increasing that number, but what else have I done? I've also increased that number, right? It's a ratio. So if I just define something as this is now 5,000 milliliters, which is 5 liters, and you count them all up, 1, 2, 3, 4, 20. I have 20 fish, 20 over 5. Magically, it's 4 fish are still. So what I'm saying is that these two are exactly the same concentrations. Even if it doesn't look like it, it's the same concentration. Okay, so of all those right there, what if I just change fish to moles? Whenever I use moles, the minute I use moles, people think, oh, I'm out. I don't understand what's going on anymore. It's the same idea. Instead of Fisher, we're going to say molar. Okay, so what I'd like you to do right now is write concentration equals, just on the side, concentration equals number of moles over volume. It's a new thing I'm doing. I'm putting stuff out.
Yeah.
All right, so I have moles and I have volume. So it's the number of things I have in the volume that I have. It's still the same concept, except now I have 2 molar. So that instead of Fisher, it's molar, and that's actually the term we're going to have. And right now, nothing's changing. We're going to label a couple things on the side, but nothing's changing at all. So what I'd like to do is talk about this little thing right here. Like there's all these big ones, or this big volume with all these moles in here, but now I pack all these moles in this little volume here. So let's do a little problem right below this. So what do I have? I have 8 moles, so let's write that below, please. I have 8 moles over, now I'm going to write this on the side, 250 milliliters. What is that in liters? What do I write? 0.25, good. So if it's in the hundreds, we got to make sure that we use the decimals correctly. So this is 0.25 liters. Okay. Now, eventually, we will need a calculator if you want to punch that in. That's fine. But dividing by 0.25 is like multiplying by 4. So 8 times 4 is 32. Okay. And then it's going to be a big M. The big M is either molarity or molar. Again, you do not have a lot to write today, so whatever I'm writing, I would definitely be doing that. Okay, so that is the simple math we're going to be doing. It's a ratio, and I'm going to try to prove that to you today in many different ways so you're just understanding it better. All right, so, and there it is. So we are going to be making solutions from liquids. This is kind of creepy, but we're going to put in a certain amount, and the more that we put in there, the more concentrated it's going to be. Okay, so let's talk about that a little bit. you don't necessarily have to write this down. Hopefully this makes sense. If I say something's concentrated, we have a lot of things in it, a lot of stuff. So that's going to be what we call solute. Is solute the solid that I put into my liquid, or the the solid that I put in, or the liquid that it dissolves it in? What's the solute? Remember, is it the solid or is it the liquid? What's solute? From yesterday's notes. Is it the salt or is it the water? What's the salt, right? Solvent is what dissolves it. So if it's diluted, it means you don't have as much. Again, I'm making Kool-Aid, I use that a lot. Kool-Aid, the more deliciousness I pour into it, the more concentrated it's going to be. So the other way would be watery, right? So the other way you can change it, so I can either add more of the top stuff. So what I want to do, you can label either one of these. Doesn't really matter, you can label this one if you like. This is my solute. This is my solvent. It's truly a mathematical relationship. If I add more or less of my solute, I can change the concentration. Or I can add water. Why does that matter? The bigger the number this gets, right, the smaller my concentration is going to be. It's going to dilute it. Or you can boil it off. What does that mean? If I'm boiling it off, the water escapes, but the salt doesn't. That's why, like in winter, your car has the residue on the sides because the water evaporates off, and all you're left is with the salt. So we are going to talk a little bit today. I'm going to show you how to do it. You're not going to actually do it today. But how do you make a diluted solution if you have a really concentrated amount? This is really concentrated. If I take a section of this out, so I have a really concentrated amount, I put it into just water, and now that becomes more diluted. And that's how you dilute a concentrated solution. That's what chemists do all the time. Chemists buy really concentrated, like 4.5 liter containers, and then we dilute it. Some other sciences, like biology, they may pay for something that's like 2 molar HCl, and a chemist would buy it as 12 or 16 molar right away and dilute it, because we're not going to pay somebody to put water in it to just dilute it. We can do that ourselves. But every science does certain shortcuts or not. So just as an example. So what I'd like you to do is, down below all this then, nice big box, write this. This is where it all comes down to. What I love about this equation is that it actually tells you all the units. It's probably the simplest equation and the easiest one to use. Molarity, which is M, equals moles over liters. Now this is technically what it is, so if you want to do any extra labels, you definitely can. But molarity equals moles of solute over liters of solution. But when it all comes down to it, the nuts and bolts of it, it's moles over liters. That's all you need. Some of you may be not as strong about understanding if you're not solving for molarity. How do I rearrange some of this? So here's a way you can think about it. If you like this idea, you might want to write this down, even if you don't feel like you need to use it later. What this shows is, let's say I'm solving for molarity. That's easy, because it already tells you. Covered up, it's moles over liters. But if I'm solving for liters, how do I solve for that? It's moles over molarity. And if I'm solving for moles, it's moles times molarity. Molarity times liters. I can even say it right. So sometimes a relationship like that is really nice to do. I know physics, they do that a lot, and sometimes in certain electric wiring and currents and things, they have a lot of relationships like that. Just makes it easier and faster. Okay, so I want to do a problem. So whenever you see that, it's going to be on the right side of your worksheet or your little note sheet. So we're going to do one right now. It says, how many grams of NaOH are needed to make a 1.4 molar solution in 465 milliliters? So I want to make a volume of that. So I need to know how much stuff I need to make that, okay? So what I'd suggest is kind of writing it the way I have it. So you don't have a lot of space going up and down, but you do have a lot of space going left to right. Okay, so this is what I'd suggest first. Let's just write down our equation ones, just so we're like, okay, those are the things I'm working with, okay? So I'm doing the first example on the right side. Okay, so it says I have 1.4 molarity. I'm going to just write it where it would be. So that's my molarity. And I have 465 mils. Again, the equation is written with units. So I'm not writing 465, I'm writing 0.465 liters. And that means I don't know moles. In fact, I'm going to write that in a different color. Okay. Well, the question's asking grams. You are totally right. But right now, all I can do is solve for moles. I'm actually doing a harder problem than maybe I should start with, but if you're understanding this, then you're going to be able to understand anything on here right away. So maybe the problem is just how many moles do you need. No one measures in moles. Like, oh, hey, get me 3 moles. That's not what you do. You get masses. You get things like that. So what do I do? If you're confused, again, you have this on your sheet. I got to solve for moles, so that means it's molarities times liters if you struggle a little bit or sometimes confuse things with your algebra rearrangements. So I have that many moles. And if the question was asking for moles, I'm done. But it's not asking for moles, I'm asking for grams. So you can either get frustrated and go, I'm out, or you can continue to try to remember, okay, if I have moles or grams and get to the other one, all I got to use is the molar mass. How do I use it? Start with a T-chart. Even if you don't have this memorized, you can figure it out. And this is how you, I can't move anything. This is how you figure it out. This unit must go on the bottom, right? Moles have to go on the bottom, so that means molar mass goes on top. It's always whatever it weighs on the table and 1 mole, and I'm done. So it's going to be 1, this is 40, and I move forward. Just as a quick skim done through just a little bit, not too long though. And I get roughly, well, let's just write down right now. Okay, so that's it in its most simplistic form. Can you figure out what you would need to make a solution? So I would drop or weigh out about 26 grams of NaOH, and I would dilute it and make a solution up to 465 milliliters, stir it all up, and it would make that concentration. Molarity is just a concentration, just a ratio between solute and solvent. Okay? All right, let's do one more. A little different. This is how many liters are needed to make 0.46 molar solution if there are only 3.45 grams of lithium chloride. So you go into your stock room, and this is all that you have for lithium chloride, but you know you need to make that. So again, if you're thinking about, well, what am I using? Well, I have this. It's asking for liters, right? So I must know moles. I must know moles. So how do you get moles? Oh, they gave me grams. So this time I got to go a little backwards, and I got to get moles first. So away we go. Let you be your guide. How do you know to put it on the bottom? Because it was on the top in the previous step. So 6.9. Roughly 42.4. After this, I'm going to have you start calculating more. Hopefully you're not waiting for me. So what do? I plug that in, right? So that becomes the moles right here. And I'm looking for liters. So again, if you struggle with rearranging this, use the triangle. I'm looking for liters. Oh, I cover up liters. It's moles over molarity, right? That's how I would do that. So moles over molarity. Get. The question is asking liters. If it asks for milliliters, I hope that we would understand that that is just simply that. Okay. You do have to be able to go back and forth with that. That can't be a question later. Well, how many milliliters would this be? You need to know. So, okay. So that's hopefully manageable. Considering the math that we have done, this is not overly complicated, as long as we know where to go and what to do. Okay, so I have a little simulation. Bear with me in case you might be tested or pushed a little bit on some knowledge of how things change, so hopefully this will all just make sense. It's a pretty user-friendly thing here. So I have a drink mix here, okay, and this is a concentration meter. And if I add a little drink mix, voila, my concentration goes up. And if I keep doing that, starts to get darker, and it should make sense it's getting darker, but the concentration is also getting greater. Check out a couple quick things here. One, no matter where I move it, it goes to 0. It goes to 0, but it's all the same because the solution, homogeneous or homogeneous mixture, means it's all the same. So it shouldn't be like this is lower here than here. It's all mixed up. Okay, so as I go, it should make sense it's getting higher and higher. Why? Because I'm increasing my solute. So I'm increasing this number, right, and not changing the bottom. So it should make sense that when I add water from the spigot that the concentration will go down. Hey, look at that. It goes down. Goes down, goes up. Well, why? Because I'm changing those values. Why, though? Check this out. I'm going to let some out. Look at the concentration. Why isn't that changing? Both are leaving at the same time, right? It's like I'm letting both of it out. It's a ratio, and I'm just letting it. That's like, okay, this is a big pitcher, and you just drink right from the pitcher, which none of us ever would do. But if you take a little scoop and you drink it, I would assume that the little scoop would taste the same, right? So it's all the same. What would happen? Let me just get this up a little bit, or else it gets messed up. What would happen if I evaporate some of the water off? So I'm going to evaporate the water. Would the concentration go up or down? So if you're like, ooh, wait, I'm guessing, or I feel, it would be altering this number, right? I would decrease that number so it would cause this to go up, right? So let's just see that, which you are right. Should work that way. So I'm going to evaporate. Yep. So now I'm increasing the ratio. Last quick thing I want to show you. Just takes a second. Hold on. By the way, if there's less liquid here, this goes faster the concentration because then there's more solute to less. Oh, so see how it says saturated? I don't know if you can tell. You see the little bubbles on the bottom or circles? So it's collecting now. So, I mean, if you took Kool-Aid mix, eventually, hey, I got lemonade. I'm just pouring and pouring and pouring, and eventually I'm stirring. And I can't dissolve it anymore. There is a point that you can't dissolve it anymore. I mean, you're like, oh, it's just starting to get good. I like the mounds on the bottom. Maybe. But it can't hold anymore. So it's saturated. So it should make sense that if you look at the concentration, it's not going up anymore because I can't fit any more in. But the minute I add water, it doesn't go up. Why isn't it going up? Well, it has to still dissolve before, like the water still can't hold enough. Oh, there we go. Now that all disappeared. And now it can start to lower because now I'm adding more. So you can play around with this, and it's just a simple app. But anywho, wanted to show you that. Okay? All right. Don't have to write any of this down. I want to just talk about how you make a solution, though. There's different kinds of glassware. So I have a beaker, graduated cylinder, and volumetric flask. I think you know what those all look like. This is a very tiny beaker, but always people are like, well, why are there numbers on there? It must be accurate. Well, it says that it's plus or minus 5%. 5% is a lot. It means you're off by 5%. These lines are just estimations, but basically they're good for holding things. Like they're really nice to hold things. It's not really for measuring. A graduated cylinder is plus or minus 5 milliliters, but a volumetric flask is accurate to only 0.2 milliliters of air. That's really accurate. So when you want to make a solution, you want to use a volumetric flask. Well, what does that look like? Let's talk about that in a second. I think you all know about this. When you're filling something up, the water, anybody know the term? What does the level of the water make? You may know that actual word. Looks like a contact lens.
I know what you're talking about.
Meniscus, yes. It makes a meniscus, right? Does anybody know why it does that? It's what? Surface tension? Kind of about that. It's a little different, but actually it's related if we go deep enough. But if this was mercury, which we can't do that in school anymore because now we can't ever be, we always have to be safe. Mercury is toxic, I get it. But I had a college professor, we broke a mercury thermometer, and he's flicking and playing with it on his palm, and he's like, look, see? And then I learned later, like when it soaks in your bloodstream, you become crazy, which I'm like, oh, that explains a lot of things. You've been playing with mercury. A lot. But the reason why it does this is it's actually attracted to the glass. So it actually goes up and creeps up in the glass. So then you would assume then that means mercury is completely unattracted or almost repelling itself away from the glass. So what do? We always measure at the bottom or the top of that meniscus. So you measure it right there, you measure it right there. What the actual shapes look like is that. That's a little harder to see, but this is actually what a mercury one would look like. Looks really weird, but that's what it would have to be. Okay, so there's a school in somewhere in southern Wisconsin about 8 years ago that some kid broke a mercury thermometer, and it somehow got aspirated up in the air, and it got over. If it gets on you, like a hazmat team has to come, and you have to go through like literally like these like plastic tunnels, and they spray you down, and you like your clothes, you gotta throw your clothes away because it's all toxic, and they had to call buses back. Like kids were off on buses going home, and they had to bring everybody back. All sports teams got canceled that night, and it took like hours to decontaminate like every student. So you cannot have mercury.
Wasn't there like a mercury spill on like a school oil thing, like in Green Bay? Some like little kids had like some mercury or something.
You might have. I'm not sure. Not good, regardless. All right, so this is what a volumetric flask looks like. It's a single line. So graduated cylinders, why it says graduated? Because it has different marks, and you can move up as you go. Hence graduation. You go through different grades. But this one's literally one. So what you do is you put a solid in there. Okay, this is what a graduated cylinder looks like. This is 1,000 milliliters. You put a solid in there. Actually, you should put liquid in there first. Then you put a solid, and then you fill it only halfway. The reason why, if I fill it all the way up to the top, I can't swirl this. Like if you put a solid down here and then you're like, I want this all, I can't move the liquid. And then you'd have to do this, which I've had to do for like half an hour as the solid trickles down and then it goes back. It takes forever, but if you only fill it halfway and use this, it dissolves in minutes, right? This is just food coloring. I figure all the commercials, whenever they're doing liquids, they always do blue. Every commercial that does that. Bath tissue, blue spray. Look which one holds more. Oh, yes, blue. So, anyway, you fill it up, and then once it's dissolved, what do? You fill it up all the way with like a wash bottle or something like that, all the way up to the line, and the meniscus touches the line. And when you hit that line, it's exactly 1,000. Well, wait, I don't want to make 1,000 mils. I want to make less, or I want to make more. That's the problem with a volumetric flask, is that it only makes one size. So, you could go bigger, and I've seen 4 liter. I mean, it's huge. It's like you are working. The liquid gets out of control. They're expensive because they're calibrated. Or hey, I want to make small. Again, one line. That's it. It's not like, oh, I'll go half. It's not half. There's no half. I want to go 250. I want to go 100. I want to go 50. Or I want to go 5. Yes, you are. You are so cute. Yes, you are. That's 5. I got this when I was getting out of college. They were going to throw this away in a lab that I was in. And I'm like, oh, I'm taking that. So there's a little line right there. It makes 5 milliliters. Very, very accurate. Very cute. So 5 milliliters to 2,000 milliliters. But there's other things that are called volumetric. Like these are pipettes. So like a normal pipette, it doesn't really have anything on it. It's just called a pipette. We do have some graduated pipettes that have little marks here, and then you suck up a liquid and you get a mark, right? Well, there's volumetric pipettes where you actually have a mark on here. So this is 25. It fills up 25 milliliters. This is 10. So it fills up to that line. This is a whole milliliter, 1 milliliter. And he's like, why would I ever do that? Some things you have to be really accurate. So how would you do that? If I want to pull out a liquid, in the past, kid you not, you put this in there. Of course, it's not going to fit. Oh, it hit. Barely. Let's see. You would actually put your mouth on here, suck it up, and then put your thumb on top, which I'm not going to do because that's not smart. And then they got a bulb, and eventually, and you'd squeeze the bulb, set it on there, let it go, and it'd create a vacuum and bring it up. But now they've created pipetters. Great name. What does it do? It pipettes. And you just pull it up, and it sucks it up. And then what you do is you pull it out of there, push it down to the line, and right now I have exactly 10 mils. And if I wanted to transfer it for some reason, I can either push this button and let it slowly out, or I'm impatient, so I just push up, and it forces it out. And I could get exactly the amount, so that's like 10 milliliters, or I could do 25. I've seen 50. It doesn't go much bigger than that, but again, in certain labs or things like that, you got to be really, really accurate. So that's kind of what they do. So here's another look of a more actual, right, meniscus. That's what it looked like. All right. Okay, How do you make a dilution though? This is what we're going to go to next. So we have some real simple calculations. Again, you don't have to draw anything yet, but if this is really concentrated, so I have a really concentrated amount, and now I want to make a diluted amount, but I need an exact amount. How do you do it? So you pull, we've already slightly touched on this, you pull out the concentrated amount, you put that in there, however much you figured out, and then what do you do? What do you fill the rest of this with, do you think, to dilute it? With water, right? You wouldn't fill, oh no, keep pouring it in. Well, then it's the same. Oh yeah, I'm gonna pour all this into there and be done. Like, you didn't do anything. Like, you gotta dilute it, okay? So then that would be diluted, it's lighter, that would be more concentrated. So let's talk about how we dilute. Don't worry about any of that. Don't worry about any of that. Okay, so you can write this in different ways, and I'm gonna write it in different ways as well, but I'd like you to put a big box, there you go, the box. And I call it M1V1 equals M2V2. Sometimes we say MAVA, which is acids, and then MBVB, which is base, but it's molarity times volume equals molarity times volume. And I'll show you how this all works with 3 different kinds of problems, okay? So C is like the concentrated, D is the diluted. I worry less about that and worry more about just have I linked my 2 together. Is my M with the right V? Is my V with the proper M, okay? So we're going to do 3 problems on the right side right now. Okay? So it says I have a concentrated H3PO4, which is phosphoric acid, and that's 14.8 molar. What volume of concentrate is required to make 25 liters of 0.5 molar H3PO4? So let me try to reword that. I need 25 mils of 0.5 molar. I go in the stock room, all I have is 14.8, like really concentrated stuff. How much of that do I need to pull out to dilute? So it doesn't need to be in this order, but I'm going to try to do it in this order. So that's my concentrated. I'm going to do it up here just so you can see it. So I have 14.8 molar. I'm just mirroring this, so that's my M. I don't know my V. If you want to call it VC for this first problem, that's totally appropriate, just so you can see it. And then all I do is I equal, okay? I want 0.5 molar at 25 liters. This is about the simplest equation that we can have. All you're doing is multiplying on one side, dividing to the other, right? So let's figure this out. Units, all I gotta do is match. So if I have liters, then I'm using liters. If I have milliliters, the answer will be in milliliters, so they just cancel out. So I take 0.5 times 25 divided by 14.8, and I get and how do I know it's liters? Because it was liters here. Oops. So if it's liters there, it has to be liters here. So what I would do, you guys, is I put that in a 25 milliliter, I don't even know of a container that ever was this big, but I put it in a 25 liter container. I drop that much, just under a liter, and then what would be the rest of it? 24.1-ish liters of water, right? And then it would dilute it, and that would be done. So this is what my typed up, I know I didn't realize I had the answer that I typed it here, but same exact look. Like that. Okay, let's look at another one. So by the way, this I just put it, okay, you don't have to write this. You'd measure out, like how would you make that solution? You'd measure out the liters of that in a separate container. You put some water in first. I know you don't know this, but I'm telling you now, it's crazy. If you put water in here, you should always do about half of this filled with water. When you put a concentrated acid in there, concentrated acid, when it first comes in contact with water, makes a real violent and crazy reaction, and it gets extremely hot. So hot, I've actually burned the pads, the tips of my fingers touching the glass when I made certain solutions, like diluting sulfuric acid. Holy cow. Like, you can't even touch it. It's like, oh yeah, it's hot like coffee. It's crazy hot. I burned, actually had, my tips of my fingers were sore for days. It was bad. So you add some water in there, cold preferably, so it helps cool that down faster. Then in a hood, fume hood, you slowly pour it in there, and then actually you should swirl that around, fill it up to 25, and then you're done. Okay, so let's do another one. Here we go. This one's a little different, so bear with me here. Okay, you have 75 mils of hydrofluoric acid, 28.9 molar. That's crazy concentrated. We used to have hydrofluoric acid. They've taken it from us. This stuff's really, really dangerous. It's in the movie or in the show Breaking Bad. They use it to, let's say, dissolve mammals and metallic objects. You need 15 mils, or liters, sorry, of 0.1 molar HF. Do you have enough to do the experiment? Okay, wait a minute, I have 4 numbers here. So if I'm thinking this, by the way, and I'm going to use 1 this time and 2. So if you want to do this with me. Like, I have 4 numbers, what the heck? I don't even know what to write. Well, this is what I need. So I'm going to write this. I'm going to do this a little different than I did last hour. Please, oh wait, how did you know it was a 2? It doesn't matter. That could be a 1. In fact, I probably should have put that as 1. It doesn't matter, as long as they're linked and connected. So, what it's asking, do you have enough? I go in there, this is all I have. So what's enough? Molarity or volume, do you think? What does enough mean? Do I have enough? Do I have enough of 28.9 molar, 75 mils? Which one, what is enough? The volume or the molarity? What does that mean? The volume. Well, why can it be molarity? Because that's already the concentration. It's how much can I take out of it. So this is how I would do this problem. Is I will solve for V. And I know we just did that problem last time like this, but it could, again, be flipped. And what I'm going to do is see if I have enough of what I have in my stock group. So calculate that. Let's see if we have enough. And I want to see if you can interpret the numbers correctly. Save that. What's another way I can write that? What is that? 52 mils? Is that right? Mm-hmm. Yeah, let's write it like that. So do you have enough? You need 52 mils. You have enough.
Yes.
Right? You need 52, you have 75. So you can go back in the stock room like, oh shoot, I needed 52 to make this. I have 75, I'm good, I'm clear. Okay? So that's how we could also use that. Unfortunately, these 2 last problems kind of were really similar. So I wanted to do one more, just a little different look. I had it showing up, actually put it in there and then figured out, by the way, why are these multiplied together? You do molarity times volume, you get rid of the liters and you're left with moles, so it's the amount of stuff you have. So we'll talk about more of that later. All right, so that's the main equation. If you haven't already written it, if you have it down, make sure you just box it. If you already have the C's and the D's, that's fine. Just make sure it's boxed. And we're going to get to our last problem. And then I'm going to do 3 homework problems for you already today. Okay? We are kind of assigning things during this first part of this ending of the year and giving you ample time to finish it on your time, mostly with this 3-day weekend and some other things, just if you wanted to get a head start instead of giving it to you and then only giving you like 2 days. So I don't want to write a thing. I want you to try to figure this out completely. Suggestion, whatever you're given, try it this time. I like to group the things that I have together first, even though I haven't been doing that yet. So it doesn't matter about 1 and 2. I like to try to solve for 2 if I can, even if it's worded differently. So try to group a molarity and a volume, and then another molarity and a volume, and then just put them in the equation. What you should see then is something like this. Right? And then one of those won't be. If I'm solving for molarity, oops, maybe I have an M right there and then the other numbers, right? If I'm solving for volume, and I have maybe a V or whatever. So put the numbers into the equation first, and then calculate it. So what volume of 15.8 molar nitric acid is required to make 250 milliliters of a 6 molar solution? Okay? So doing that, I'm going to hand out your worksheet, which we will do a couple problems for. if it is in milliliters, it's okay to keep it in milliliters. Well, but molarity is in liters. That is true, but all the units cancel out. Or whatever's left is whatever's left in a relationship such as this. So you need about 94.9 milliliters. Again, what would be the rest of it? You make a 250 milliliter solution. The rest of that volume is water. Distilled water, purified water, something like that. Okay. All right, let's take a look at the front of your sheet. I've grouped them together on purpose. I think that's all I have. Oh, yep. All right, so I want to do all the B's on the front. Each one is different. One says mass, one says molarity, and one says volume. And I tried to have kind of a theme and the same approach so you get a little extra practice trying to solve for each of them, because those are the three variables that we have for their equations, right? So first one says, what is the mass of the following chemicals is needed to make the solutions indicated? 2 liters of a 1.5 molar sodium nitrate solution. Okay, I want mass. Well, first, on my sheet, personally, I would have two things, or at least one of these two things written down. I'd have either that, or you may even want this guy right here. Just so it's somewhere on the top of your sheet, just helps expedite everything for you. So that's what I'm using. I like to plug in everything and where they go. This gives me a better visual. Okay, I can kind of see what I have and what I don't have. So that's what I have. So right now that problem's solving for moles. As we practice though, that's not necessarily where I end. I want mass. So first, hope we'd all agree, that'd be 3 moles, 2 times 1.5. But again, if you're confused, solving for moles, you cover up moles, molarity times liters. So how do I get to grams? Don't fight it, go with it. I just make, like what I would do is just have it and then go right off of my answer and go with the T-chart. Oh, moles go there. Yep, it goes to the bottom. There's one of those. So sodium is 23, or approximately. Nitrogen is 14. Oxygen is 16 times 3. That cannot be what that was way off. That's better. Get 85 times 3, and I get and if you look on the bottom, oh, there's the answer. Oh my gosh, they just keep giving.
It says something. It says 272.
Yeah, that's for 1A.
Oh, yeah. Yeah.
But now you know the answer for 1A.
Yeah.
So that's how you do the first problems. Okay, let's go to the next one. It says calculate the molarity. Now, check it out. I give you grams. What is that going to get me? Moles, right? So I'm actually going to do that first. I can't even engage into that relationship until I get into moles. So that's actually what I'm going to start with. We even give you the formulas. My gosh. It's almost like there's no work at all. Molar masses should not be any kind of an issue. You have a calculator. You just look at it. You just type it in. Don't shortcut too many digits. At least go a decimal. You have it in your calculator. It's not about being lazy. It just, well, actually, that's really being lazy. I can't push one more button. Hopefully that's right. Oh, done. I'm not done. I was like, wait, that's not the answer, because I'm not done. That just gets me moles. I was so excited. And now I keep typing this in. Sorry, a second. There we go. We'll ignore that number. How scary that is. My car I drove in high school was some letters and then 666, so I always called it Lucy, or Lucifer. What I would do then is this. I would actually just put a line under there, and then what can I put? What goes underneath it? The 2.0 liters. Boom, there's my moles over liters. I can solve for molarity right there. Right? The unit for molarity is a capital M. Make sure it's a capital M. Lowercase m is something different. It's usually mass. Okay? All right, one more. Volume. Again, oh shoot, come on. You gave me a mass again. Yep. Trying to make sure that we're getting this. These are as hard as I can make them. A lot of times they would just give you moles and you just have it. So if you can handle this, you're good. So last step. All right, we're going to put that in there. Then, I'd like you to try to do a little bit of this. And I want volume. All right, so I'm going to solve for L. Look it up. Oh shoot, I don't know how to solve for liters again. Use the triangle. Cover up liters, see what's divided or multiplied. You should be able to get it. I know my answer is a little different on the answer key, but it's close. I think I have being exactly 4. Okay, so a couple things on your plate right now. You should be finishing or starting, depending on where you're at, but you are able to work on your solubility curves. You just reading table, those graphs. Are you on the line? Where are you on the line? How many grams it is? Then start applying molarity equals moles over liters, and start applying M1 V1 equals M2 V2. And that should get you where you need to be for now. Okay, so 3-day weekend, we should be able to at least get some of that regardless where we're at. So you selling for liters, so I took moles, it's over. Hopefully you get that.
Oh, yes.
You get it?
Mr. Gussie, do you know when class is ending?